David Smith here with one more Flip Classroom math video. 3 tips before you start. First, you could speed up or slow down the playback if that helps you get through the video at your own pace. Second, you could pause the video at any time to catch up with your notes. Third, you could turn on the captions and watch my words go by on the bottom of your screen.
In today's lesson, we're going to dive into equations for tangent lines and normal lines. So let's review the overall territory, and to do that I'm going to use this graph right here. So check it out. What I've done is I've graphed some function, f of x, and then that's in black, and then at point A, I've drawn in a line that's tangent to the function at point A. And remember, a tangent line touches a curve at only one point, does not cross the curve. And then finally, in red, I've drawn my normal line at point A. And the normal line is 90 degrees to the tangent line. So it's coming out exactly like that. Now let's take a look at some of the things we know about this situation. Line L is tangent to f of x at point A. The slope of line L is the value of the derivative of f of x at point A. So as you recall, there's a subtlety here. What we do is we first find the derivative function of f of x, and then we plug the x coordinate at point A into the derivative function to find the value of the derivative. So what I've specified here is value of derivative, and that's commonly just referred to as derivative, as we'll see in a minute. But you'll have to remember to differentiate between the derivative function, which is a function that then can give you the derivative itself at a point. So derivative is always taken at a point. Now let's take a look at this normal line. This is 90 degrees to the tangent line. So there's something about its slope. We know that it's the negative reciprocal. This digs back into your stuff probably in Algebra 2, Algebra 1, where you dealt with perpendicular lines. They're related, their slopes are related by the negative reciprocal. So that's what I've written here, and I've written this little statement here, 1 over the derivative. Again, that's the value of the derivative. That's how we take a negative reciprocal. We just put whatever this is on the bottom of a fraction with 1 on the top and put a negative there. Okay, so that's the territory. Now what we're going to do is we're going to do some examples where we find equations of tangent lines and we find equations of normal lines. All right, let's take a look at a problem. Here's a prompt that you might get. For f of x is 3x squared minus 2. The prompt is find the derivative of f of x at x equals 1. So this is a 2-step problem. The first thing you need to do is find the derivative function of that function. Then once you have that, you plug 1 into the derivative function, and that will tell you the value of the derivative. So you have all the tools to do that. Pause the video right now and do that calculation and come right back. Okay, let's see how you did. So the derivative function, using our power rule, we just multiply the 3 by the 2, that gives us 6x. We lower this by 1, so x to the 1 is just x, and then the constant just goes away. If you can't remember why that goes away, I have some videos a couple lessons back that talk about how to use the power rule with a constant. So here's our derivative function. That was step 1. Step 2, take the value of x for which we're looking for the derivative, plug it into the derivative function. So that's f of 1, so I plug 1 in for x, and the value of the derivative of this function at x equals 1 is 6. All right, let's finish this up by finding the equation of that tangent line. So here's your prompt. Find the equation of the line tangent to the function at x equals 1. Important reference there. We could change this, and you would have to do a little bit more work to find the equation of that tangent line. But in this case, that's all we're doing. So go ahead, pause the video. You have enough stuff to do that. So I want you to gather your information, do your calculation, and come back. Okay, completing this step does require that you dig back a little bit into the particulars of what makes equations of lines. So we already have our slope. Remember, the derivative is the slope at the tangent point. So this step gave us the slope of the tangent line at the point x equals 1, where x equals 1. Okay, so that's our m equals 6. Now, to find an equation of a line, what we would need here would be, we have a slope, we need just one point on that line, and that would allow us to write the line equation. So what I have to do is I have to take my 1 and plug it all the way back into my original function to get the y coordinate of the tangent point. So I just did that here, f of 1. Notice I'm not doing f prime of 1, I'm just doing f of 1. Put that together. That gives me my y value of 1. So my tangent point is the point 1, 1. Now I have a slope and I have a point. And these are both on the line of tangency. So now pause the video, use this information to write the equation of the tangent line. All right, to do this, I had to think about forms of equations of lines. And one of the most common one is slope-intercept or gradient-intercept. And that's just y equals mx plus b, where m is our slope, which, hey, we already know that, and b, that's our y-intercept. We don't know that, but we can find that really fast. So what I'm going to do is a plug-in step with this, with what I know, and that's going to leave us with b as the only variable which we can then solve for. So check this out. Y, which is 1, the y coordinate, is going to be 6 times the x coordinate, which is also 1. I just plugged that in there, plus b, which we don't know. Now I can just rearrange and solve for b. That gives me b equals -5. So that's my y-intercept of this function. So now I can just come back to my y equals mx plus b, and it's m, which is our slope, x minus 5, because our b is -5. Okay, before we go on to finding the equation for the normal line, let's summarize what we did. Here's our function, 3x squared minus 2. Here's our derivative function, 6x. And then here's what we figured out. The tangent line at the point 1, 1 is y equals 6x minus 5. So that's the work we did on the last board. So here's the new prompt. Find the equation of the normal to the curve at x equals 1. So a couple things to unpack here. The normal to the curve is the normal line. And notice how they're just saying at x equals 1. They're not telling you the coordinates of that point. They're just saying when x equals 1. So if this was a problem where they didn't give you this information here and they just gave you the function, you would have to do these steps. And perhaps more importantly, or more of a challenge, you would have to remember to do those steps because you're going to need that slope and you're going to need that point in order to answer this question. Okay, now let me remind you of a couple things from the very beginning of this lesson. The slope of the normal is the negative reciprocal, or 1 over the derivative of the slope of the tangent line. So go ahead, pause the video, and tell me what the slope is for the normal. I'm just going to say n normal. And what is that slope going to be? All right, so I just took the negative reciprocal of my derivative function, which is 1/6, -1/6. I can take that right there. And again, it's at the point 1, 1. So we know that as well. Okay, so now pause the video. Use the steps we did at the very end of that last board to find the equation of the normal. Okay, I did the same technique before. I took my y coordinate, put it over here where y is. I put my slope, my -1/6 there. I plugged in my x coordinate for the x part, and I left my b alone because I don't yet know what that is. I worked through my equation. I get b equals 7/6. So then again, in gradient intercept form, I got y equals -1/6x plus 7/6. Now, before we go on, I want you to pause the video and convert that to standard form, just for practice, because you are going to see those prompts from time to time, and you need to remember how to do that. All right, my first step in this is always get rid of the fractions. So I have a bunch of sixths here, so if I just multiply the whole thing by 6, every term by 6, I'm going to make those fractions go away. So that gave me 6y equals -x plus 7. Now I just have to rearrange it so my x starts and is positive. I've got my 6y minus 7 equals 0. That's the standard or general form equation for this line. Okay, let's move on to a more complicated problem that nonetheless is going to use the same techniques we just went through. So here's our prompt. Find the equations, so more than one equation, of any horizontal tangents to the curve. Now, what that means is that we're looking for equations of tangent lines that are horizontal to this curve. Now, part of this is going to hinge on understanding this curve. we have a cubic term here, so that makes it a power function. And all power functions have this characteristic. So now I'm going to pop over to a Desmos screenshot and take a look. You can see on the left side, we have a maximum. That's where the curve peaks out, but then drops back down, kind of like an upside down parabola. However, it doesn't just keep going down. As you notice on the right side, it has what we call a local minimum, where it curves back up. So this function, domain and range are unrestricted. X and Y can get as big or as small as they need to, but we do have a local max on the left side and a local minimum on the right side. Okay, let's get back to our function and our problem. So what they're asking us to find is the equations of any horizontal tangent lines. So on that curve, a horizontal tangent line is going to be tangent at that local max and that local minimum. Now, what is the slope of those tangent lines? Think for a minute about horizontal lines and their slope. Okay, if you remembered that horizontal lines have a slope of 0, you're correct. Now, we're going to exploit that fact in a minute, but first, we need to find the derivative function for this function so we can continue the problem. We're looking for slopes of tangent lines. That means we're going to take the derivative of the function of the actual graph. So pause the video, take that derivative, come back. All right, here's our derivative function. I just used my power rule on every term, got down to that. So, and I'm using the notation dy dx because I started with y, so this also means the derivative function. However, we're just using different notation. So you should be familiar with that. Sometimes your prompts will use this. If I'd written f of x here, we could just write f prime of x there. Same thing. Okay, so now, this calculates the slope of the tangent line at a point. Now, ultimately, we're going to need those points. So check this out. This has to equal to 0. And then we can solve for x, and that'll give us our x coordinates for our points. So check this out. If I just write 6x squared plus 6x minus 12 equals 0, this is a quadratic function that I can solve and find the roots for. And that will give us the x coordinates of our points where the tangent line is 0. So go ahead, pause the video, solve that for x. All right, here we are. The easiest thing for me to do, I mean, you could factor this problem, but it's going to be way easier if you just divide everything by 6. Then I get x squared plus x minus 2. That factors down into x plus 2 times x minus 2. Again, we're all equal to 0. So this solves to give us x equals negative 2, and then this one solves to give us x equals 1. So these are the x coordinates at the point of tangency. Now what we need to do is figure out the corresponding y-coordinates for those points of tangency. Now, if you remember from the last video, there's a certain step that we do to do that. Go ahead, pause the video, find your y-coordinates, and come back. Okay, I took this problem all the way to the finish, including giving you a graph. So let's walk through that. So I summarized what we learned from the last board. Here's our original function. Here are the x-coordinates at the 2 points where the tangent line has a slope of 0, where it's a horizontal line. So to get the y-coordinates of those points, because that's what I'm going to need to come up with those line equations, I plug in my x value at the point of tangency into the original function here. So I just did my plug-in step, and that gives us a y value of 21. So that point, that first point of tangency, is the point negative 2, 21. Then similarly, with the second, I just plug in 1 in for x. Right here, there's my plug-in step. That winds up being negative 6. So the second point of tangency is at 1, negative 6. Now that makes sense with the graph we looked at in Desmos. That's roughly where those points were, or I should say exactly where they were. So now, coming up with the line equation. Now remember, horizontal lines have a 0 slope. So the y-coordinate of a horizontal line never changes. So the form of a horizontal line equation is y equals something, i.e. that non-changing coordinate. And so for the horizontal line that goes through this point, the equation is just y equals 21, never changes. And then for this point here, it's y equals negative 6. Now I've sketched our solution on the graph so that you can see that graphically. So check this out over here. Here's a rough diagram of our power function, and I've labeled my 2 points. Here's my local maximum at minus 221. Here's my local minimum at 1, -6. And I've sketched my tangent lines. So these lines are horizontal, tangent to the curve at those points. And here's my equation for that one is y equals 21. And my equation for that one, y equals 6.
Now that you've watched the video, take a moment to jot down any remaining questions so you can ask them in our next class. If you want, you can come back and watch the whole video again if that helps deepen your understanding. If you enjoyed the video, please click like or subscribe.